The success of RAM virtualization comes from effectively sharing computing resources, including hardware accelerators. However, there is an important challenge. The physical layer tasks involved in the distributed unit of a base station has tight and hard latency constraints. When DUs share computing resources, there is no deterministic computing performance anymore, which means that meeting these latency constraints cannot be guaranteed. Let's analyze in more detail the root of the problem. Every 1 millisecond, a DU receives OFDM symbols from the radio unit encoding one uplink subframe. This uplink subframe carries control and data channels, including all the data transport blocks and control feedback sent by the users. Processing these channels consists on a set of operations such as demodulation or forward correction coding, which are compute intensive. Only once all these channels are processed can we then make scheduling decisions, and not before, because the uplink data and control channels carry information that is needed to calculate the scheduling grants, such as feedback from the users about their buffer states or the quality of their channels. And only once all the scheduling grants are calculated, we can then process a downlink subframe that includes all the corresponding data and control channels, among other important signals that preserve synchronization with the users. 3GPP imposes latency constraints between uplink and downlink channels. This latency constraint implies a hard deadline to process every single job, which is usually equal to 3 milliseconds. In shared computing platforms, we do not have deterministic computing latency anymore, so it may well happen that some tasks, especially those more compute intensive that involve processing data channels, may occasionally take longer than expected and cause that the whole job violates its deadline, as illustrated here. As a result, a downlink subframe containing important control and synchronization signals cannot be delivered to the users when they expect it, and therefore they lose synchronization with the base station. To demonstrate this problem live, we have set up SRS InnodeB, which is an open source full-fledged LTE stack that implements the baseline pipeline we just described, transmitting and receiving regular IP traffic to and from a regular UE on a shared computing platform with 5 Intel CPU cores. We refer to this InnodeB as DU under test or DUT. Sharing the same pool of CPUs, a set of Intel FlexRAN instances, which we refer to as competing DUs, generate competing signal processing workloads. Note that we rely on the legacy Linux scheduler, and the threads of all the DUs have the same priority. This is the dashboard we will use to visualize the demo. No DU is deployed in the platform at this point. We first deploy the baseline DU under test, or DUT, by selecting baseline and pushing the start button. A number of graphs in our dashboard monitor different performance and state information of the platform. These gauges indicate that the DU under test, or DUT, is the baseline DU. These two graphs show the time evolution of the DUT's network throughput, downlink throughput at the top, uplink throughput at the bottom. In turn, this graph displays the 99th percentile of the processing latency of each pipeline in DUT. A red line indicates the time constraint to process each TTI job. If we violate this threshold, the user will have problems synchronizing with the base station, as explained before. The bottom graphs show information about the competing DUs. As you can see, no competing DU is deployed at the moment. Let's accelerate the video. As you can see, the competing platform processes all the TTIs of the baseline DUT well below the threshold, which preserves maximum throughput at all times. This is expected because there is no competition for computing resources at this moment. Let's deploy one competing DU with high load to study its impact on our DUT. The gauge and the graphs at the bottom of the monitoring display indicate that one competing DU with high load is successfully deployed. If we take a look at the graphs monitoring our DUT, we can only observe a mild increase in the processing latency of its TTI jobs, which has no consequence on throughput. Let us now gradually deploy more competing DUs and observe their computing interference on our DUT. After deploying 5 competing DUs, our baseline DUT begins to have problems processing TTIs below the threshold with some mild performance degradation on throughput. However, as we keep deploying competing DUs, more and more TTI jobs cannot be accomplished within the time constraint, which has a huge impact on the DUT's throughput performance. Eventually, the UE disconnects from the base station, and therefore the network throughput of our DUT falls to 0. We call our solution to this problem Nuberu. The underlying idea is extremely simple. Every job, the goal of Nuberu is to make sure that the most important signals and channels, those that preserve user synchronization, can always be processed before the final deadline, the red deadline in the figure. In this way, the goal is that by this red deadline, Nuberu always has ready the minimum amount of information required to build a viable downlink subframe, which we call minimum viable subframe, and which can preserve synchronization, even if to do so, we have to sacrifice data channels somehow. To this end, we set up a hard deadline, depicted in blue in the middle of the job, to process both uplink and downlink data channels, so we make sure that Nuberu always has enough residual time for those other critical tasks that enable a minimum viable subframe. In a way, the idea is rather obvious. However, for this to work, both uplink and downlink data processing tasks need to be decoupled from the rest of the pipeline. And this is far from simple because of the dependencies between tasks that I introduced before. To break these dependencies, we rely on predictions at different levels. We designed a predictive two-stage downlink scheduling approach which let us delay downlink data during shortages of computing capacity. We designed an early hybrid ARQ approach which predicts the decodability of uplink data and lets us process uplink data without time budget restrictions. And finally, we designed a simple congestion controller that predicts the instantaneous computing capacity and adapts the grants scheduled accordingly. These approaches let us decouple data processing tasks from critical tasks and let us establish new deadlines to make sure that the latter are always accomplished. To demonstrate the ability of Nuberu to preserve reliability under any circumstances, we use Nuberu as our DUT in exactly the same scenario as before. We now select Nuberu as our DU under test and click Start to deploy it. We can observe the same graphs as before, plus an additional one. This graph shows the latency performance of the data processing workers that, thanks to our predictive techniques, are now decoupled. We can also observe that the TTI latency is now close to the threshold, even when there is no competing DUs in the system. This is because, as explained before, our TTI pipeline is split into two phases, and the second phase is pushed towards the job's deadline. Doing so has no impact whatsoever on the user's experience, but it lets us maximize the time budget for data processing workers that are now decoupled. Like before, let's gradually deploy competing DUs. As we can see, the computing interference generated by these competing DUs has an important impact on the data processing workers, but minimal impact on the main job, which is always below the threshold regardless of the computing interference and preserves maximum throughput at all times.